Okay, hi. So a couple videos on convergence of sequences of random variables, usually in our context estimators. These are the references. So mathematical statistics, not sure which edition, 9.3 called consistency, and Casella and Berger statistical inference, section 5.5 called convergence concepts. Okay, so suppose we have a sequence of random variables and another random variable y. The definition of convergence in probability written like this, we write yn arrow y with a little p up here. The definition is that if I give any small or any positive constant epsilon, that the probability that the absolute value of the nth member of the sequence minus the random variable y is greater in absolute value than epsilon, that the limit of that is 0. So in the limit yn, the probability that yn minus y is greater than epsilon is going to 0. Some important notes here are that the random variables can be constants, the RVs can be constants too, and one of the most important cases, maybe the most important case, is when y is a constant, and you're showing that the random variables are going to a constant in probability, so they can be constants. That just means it's like a degenerate random variable where it is always the same number. Okay, so this is one. The other thing is you should not think of y1 to y2 is ... not usually IID, because then it wouldn't converge to anything probably. So it's usually, what is it usually? Usually it's something like the nth partial sample mean, the nth sample mean, of the first n samples of the of another IID sample. So often special case, typical case is, and we'll get to some examples now, but typical case is, say I have theta hat n is a function of some function of a sample from y1 to yn, where the y1, maybe I should see the x just so you don't think, those have a sample x1, xn up to xn, and maybe these are IID, and we are interested in whether theta hat n converges in probability to theta, where theta is some parameter, a parameter in the distribution of xi. Okay. All right. So let's continue with this. So first example is the most important example and something we've done already. So let's just do it again so that we can bring our new definition into. So let's let suppose y1, let's write it like this, y2. The idea is, because you are taking n in the limit here, so we just write it like this usually. Let these be IID, and suppose EYI equals mu, variance YI equals sigma squared. Then if we want the probability that yn bar minus mu is greater than epsilon, I want to show maybe that this, right, that this this goes to 0 as n goes to infinity, right? That's what I want to show. So we are using this to mean this. We won't keep writing this, but so what do we know about this from Chebyshev's inequality, right? This is less than or equal to the variance of y bar n over epsilon squared, which is equal to sigma squared over n epsilon squared. And so we have what, 0, which is less than or equal to sigma squared over epsilon squared over n, which goes to 0. So y bar n converges in probability to mu, the thing it's trying to estimate. This actually has a name. This little proof we just did, this example, is called the weak law of large numbers. Weak law of large numbers. We've already looked at it. It's the big result that we looked at as an application of Chebyshev's inequality. Weak large law of large numbers. Right. Okay, so right. So the sample mean converges in probability to the actual mean, as long as the variance and the mean itself should be finite, right? This makes sense. These have to be finite for this to go to 0. Yes, you notice the requirement here too is that mu be the expected value of y bar hat. And that has been shown many times, so that's required certainly for this proof here. Okay, what's another example? Let's look at another example. What about the sample variance? Let's put a little n here to mean we mean the nth one. So we saw already, we know Sn squared is an unbiased estimator for sigma squared. Let's use the same setup as up here. It's just like a part 2 for this. So again, we can apply the same Chebyshev, same setup, apply Chebyshev, and we have the probability that Sn squared minus sigma squared is greater than epsilon, must be less than the variance Sn squared over epsilon squared. And so this is true, right? And as long as this variance goes to 0, since epsilon squared might be a small number, square very small, but as long as the variance goes to 0 with n, this will go to 0. And again, the same sandwich theorem or squeeze theorem will show that this limit goes to 0. And so we have the same result. We have Sn squared goes to sigma squared. Sn in probability converges to sigma squared in probability as long as, right? As long as the variance of Sn squared goes to 0. That's just a regular arrow because that's just a sequence of numbers. Okay. Doesn't depend on actually the random sample, does it? Right. Okay. So we have this. In fact, this is even more general. We can generalize. So generalizing, if, let's say, theta hat n is an unbiased estimator for theta, and the variance of theta hat n goes to 0 as n goes to infinity, then the same thing, let's write it just because it's fun to write, theta hat n minus theta less than the variance theta hat n, and theta hat n goes to theta in probability. So, or the other word is, did we write this up here? I can't remember. Or the other word is, yeah. So when in this case, I don't think I wrote it, in this case, when it is an estimator, so we have an equivalent way of saying it. So when an estimator converges in probability to the constant it's trying to estimate, we say, I think I may have wrote it up there, we say theta hat n is a consistent estimator for theta. Now, it can be consistent without being unbiased, as long as it converges to theta in probability. But if you want to use this, if you want to use this, right, that the variance of it goes to 0, then yeah, then you if you want to use the variance of it going to 0, let's see, then it does need to be unbiased. Yeah. Otherwise, you just have to show some other way that it converges in probability to theta using the definition. Okay, yeah, I know it's a lot. It's a little bit thick here, but I think you're doing fine. It's still, if you think about it, it's all still just that one result from Chebyshev's inequality, and just knowing what is unbiased and the forms of the expected values of the estimators and the variances of the estimators. All it is. Okay, so we showed actually for the variance that so previously, let's not do it here. We have shown that if for y1, y2, this is probably an important case. If it's IID normal mu sigma squared, those are finite, then the variance of Sn squared, the sample variance, is equal to 2 sigma to the 4th over n minus 1. So this goes to 0, and since Sn squared is unbiased always. We know. Is a consistent estimator for sigma squared in this case when they're normal, but we can actually show this is consistent. Sn squared, the sample variance, is a consistent estimator. It converges in probability to the sample variance in a much broader set of cases. First, we introduce some a theorem, and that's not terribly difficult to prove. We will, I don't think we'll prove it in this short lecture right now, but we'll just write it down for now, and then we can do this at any time later. It's basically limit laws for convergence in probability. So let's just say, let's say theta hat n converges in is a consistent estimator for theta. And you can actually make this more general, and not in terms of estimators and constants, but in terms of the more general way we set it up there. And let's call something else like, let's say, omega hat n probability to omega. Then let's just do it in as few of these as possible. Then we have that, well, the sums converge in probability to theta plus omega. I'm only doing the constant case here because I think that's all we need, but it's true in the more general case too. The product rule. And let's say G theta hat and converges in probability to G theta, where G is continuous. At theta, it doesn't have to be uniformly continuous, but point-wise continuous where you are interested. Okay, okay, so we're going to use this, we'll call this theorem. Yeah, we'll just call this theorem for now. I don't want to make the videos too long, so we will just do this general result here, and then maybe one more thing, and then we move on. So, okay. So, let's show a more general case. So fact. Yeah. Yeah. Yeah, this is nice. This doesn't even really, I don't think it uses the unbiasedness. Maybe it does explicitly, I was going to say. Okay, so let's just show this fact. Or I could make it an example, but let's suppose, so let's let y1, y2, dot, 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 iid, and suppose EYI equals mu is finite. EYI squared, let's call this mu2, the second moment is finite, and the fourth moment is finite. I'm not going to find counterexamples, but we're going to be careful and write all these things down. And okay, now we were going to try to show that then, I think that's all I need. Then Sn squared converges in probability to the variance. And the variance here is just, you can write it in terms of mu2 and mu, right? So this is just, this variance here is just mu2 minus mu squared, right? So we know it's finite, it makes sense. We'll just call it that here. Okay, so here, maybe we should write it, we'll write it sigma squared equals mu2. Okay. All right. So in other words, all I need is to know these first four moments, or these three moments are finite, and then I know the sample variance will converge in probability to the actual variance. Nice. Okay. So one first thing is that we write Sn squared equal to, well, it's equal to, let's just remind ourselves, 1 to n. And this we will manipulate as follows. Let's square this out and apply the sum. So I get 1 to n yi squared. The middle term is, all right, let's minus 2 sum yn. That could come out too. We'll take it out next time. And then plus sum 1 to n y bar squared n 1 to n. And then this is just equal to, well, this I can't do anything with, 1 to n yi squared. This one, though, this comes out the yn, and then I sum the yi, so I get minus 2 n y bar n squared, right? Because I have it come out here once, and then this, when I sum the yi's, I get ny bar n, and then I have plus n yn squared. So this is equal to the sum 1 to n yi squared minus n y bar n squared. Okay, so now Sn squared is equal to 1 over n minus 1 times this, right? Times this difference here. So let's write it like this. We want to correct that to 1 over n. So I'm going to write n over n minus 1. And I'll bring the 1 over n in here. I have 1 over n sum 1 to n yi squared minus, the n cancels here, okay, we're almost there. We're going to use the theorem next. So really it's just the theorem. Do you see what to do? It's the weak law of large numbers, a couple times here and here, and then it's just this theorem, this limit law theorem. I have a sum, I have a product, I have a continuous function, or two. So there's several little pieces here, but we have. So let's look at the pieces. First of all, let's look at this one. 1 over n times the sum 1 to n yi squared must converge in probability to the expected value of yi squared. This is just the weak law of large numbers. We just showed this, which is just equal to mu2. Okay, just showed this. Notice that if you were worried that y1 squared, I don't know if you were worried about this or not, but these are also IID, right? Because the y1 to y2 are IID. So if I square them, they're still independent. They still have the same distribution. So that piece goes to mu2. What about this? We know yn converges in probability to mu, which is e yi. And the square function, right, is continuous everywhere. So okay, that's good. That's good. So we're almost done. So finally, the third one. Now, remember, these are constants, but they also converge in probability. So if you're not sure, put it into the definition and prove this is a correct statement. This converges in probability to 1. So using the product rule, right? Sn squared, which is equal to this long thing, converges in probability to the first thing is 1 times second thing, mu2, minus mu squared, which is just equal to mu2 minus mu squared, which is just equal to sigma squared, the variance of the sample. Nice result. Okay, this is almost all the way there. Maybe we just show one more thing here. I know it's going a little long, but let's just show one more thing. So what about, so last thing. Fact Sn is a biased estimator for sigma, but Sn is nonetheless consistent. It converges to sigma in probability. So this is interesting because I have something that's biased. Its expected value is not the thing it's trying to estimate. And yet it converges to it. So in the end, in the limit, it's unbiased in the sense that it actually is that thing, or is goes to that thing. But everywhere, any finite n, its expected value is not going to be the thing it's trying to estimate. So let's show this now. We're just going to use those results we have. And this is for the case above, right? For a case above where we know that Sn squared. So where finite first 4 moments. But really anywhere, I believe, where Sn squared goes to sigma squared. Okay. So then we know, so we have the finite first 4 moments gives us, this is not hard. Sn squared goes in probability to sigma squared. Okay. Because of this. And then because the square root function is continuous, certainly at anywhere we would be taking it with respect to a variance which is non-negative, we have the square root of Sn squared, which is equal to Sn, converges in probability to the square root of sigma squared, which is sigma. Okay, that proves that Sn converges in probability to sigma. To see that Sn is biased, though, maybe this is a little more work. Yet, let's write Sn is biased. Since what do we want to do? Let's check. Yeah, so to show this, we will take the variance of Sn, which is equal to E Sn squared minus ESN squared. And this is unbiased. We know Sn squared is unbiased. So this is sigma squared minus ESN all squared. And we know this is greater than or equal to 0. Why? Because I have a variance, right? I have expected value of a non-negative quantity. So it's got to be greater than or equal to 0. So this implies, so then we have that sigma squared is greater than or equal to ESN squared. Or sigma is greater than or equal to ESN. Okay, we've almost showed it's biased, right? If I can get rid of the equal sign. Well, the only way I have equal sign, since sigma equals ESN only if, right? Only if the variance of SN is 0, then SN is biased for sigma in all random cases, so in all real cases. The only way the variance can be equal here is essentially if SN is just set equal to sigma. So for any kind of real random variables, it's going to be positive, and SN will be a biased estimator of sigma. Okay, thanks. Stay tuned. There's more on this section.